When you train a self-evolving LLM agent, its capability grows by accumulating experience. Trajectories, distilled skills, and environment facts get written to an external memory store and retrieved at inference time. In production, that memory isn't static. Cloud platforms treat storage as elastic. Quotas move with load, cost, and tenant demand. You provision memory, you squeeze it, you expand it again. But here's the problem that hasn't been formally addressed until now. When you squeeze the memory budget and then return it to full capacity, the agent's capability does not return with it. It settles permanently below its pre-squeeze level. We call this memory hysteresis. The cause is structural. Current memory management policies treat retention as a binary decision or a one-way compression. You either keep an entry verbatim or drop it. Or you compress it into a coarser representation, but only downward. Once you delete or irreversibly compress, you discard the material needed to rebuild that entry later. When the budget expands, the store has nothing to reconstruct from. Even value-based governance, which intelligently selects which entries survive a squeeze, leaves no residue. A policy that only keeps or drops entries carries a provable residual deficit floor. You can optimize which entries survive, but you cannot close the capability loop. To fix this, we need retention to become reversible. We need a system that treats memory not as a static archive, but as a dynamic state machine that moves entries up and down a fidelity ladder, scheduled explicitly by the live byte budget. That system is CrystalMem. CrystalMem operates as an elastic memory sidecar. It replaces deletion with reversible state assignment, driven by three coupled mechanisms. First, a four-state fidelity ladder that demotes and promotes entries based on crystallization energy. Second, an influence estimator that ranks entries by their actual contribution to task outcomes, coupled with a dependency graph so hub entries sync last. Third, a verified recrystallization pipeline that regenerates entries from stored residues and admits them only after passing an invariant check. All of this runs inside the serving path with explicit compute and byte caps, zero training, and a single sorted sweep per stage. Let's break down how each piece works. The fidelity ladder defines four states for every memory entry: full, compressed, skeletal, and trace. At the top, full retains the raw serialized entry. As you move down, byte cost decreases and utility delivery scales down proportionally. The key insight is that demotion is priced using a crystallization energy function. This function balances two costs: the utility you forego by downgrading the entry now, plus the compute you will spend to regenerate it later. The formula weights the current utility drop against the anticipated regeneration tokens, converted into capability cost. When the budget tightens, the system solves a constrained assignment problem. It doesn't randomly drop entries. It runs a water-filling descent, demoting one rung at a time in increasing order of marginal price, until the store fits the incoming budget. The moving boundary between demoted and retained entries is called the crystallization front. But which entries should demote first? Random demotion or size-greedy eviction both degrade performance. CrystalMem estimates entry value online using advantage-weighted influence. Every time the agent retrieves entries to answer a query, the system attributes the graded outcome back to those entries, baselined against recent query performance. Entries that repeatedly appear in above-average outcomes accumulate influence. Stale or decorative entries decay towards zero. This isn't just a local score. Entries are not independent. A skill cites facts. A trajectory grounds a distilled rule. CrystalMem maintains a dependency graph over co-retrieval and reference edges, letting influence flow across it. Hub entries that anchor other entries absorb value from their neighbors and are protected from early demotion. As a hard guard, an entry cannot sink below skeletal while a full neighbor still cites its invariance. When the budget expands, the system doesn't just guess what to restore. It runs verified recrystallization. The system selects a promotion set using a greedy knapsack approximation, maximizing utility regained per regeneration token, constrained by two hard limits: a fixed share of serving compute and the available byte headroom. For each selected entry, the host model conditions on its stored residue and graph neighborhood to draft a reconstruction. But the draft is never admitted blindly. A verification operator checks the regenerated entry against the invariance stored at demotion time. Every key span, entity tuple, and outcome fact must be entailed by the draft. If it fails, the entry stays at its current rung. This gate prevents hallucinated reconstructions from polluting retrieval. Admission converts serving tokens into recovered capability, which is exactly the storage for compute exchange the ladder was built to support. The theoretical guarantees are tight. The water-filling schedule is provably near optimal for the fractional relaxation of the budget constraint, with rounding error bounded by the span of a single entry. The promotion pass admits the same argument per binding cap. And under exact regeneration, the residual deficit converges to zero. The loop closes. We validated this across 7 environments spanning retrieval, long context dialogue, agentic control, and synthetic drift. We tested against 17 methods, including LRU, MEMGPT, R3MEM, Curator, and 5 value governance baselines, across 6 backbone scales from 3B to 72B parameters. The results are consistent. CrystalMem achieves the highest restored capability in every setting. At equal budgets, it leads the strongest binary baseline by an average of 4.6 percentage points. The hysteresis area drops to 0.013, compared to a baseline range of 0.044 to 0.216. The residual deficit falls to 0.5 percentage points, while the best binary policy still forfeits 6.6 points. The gap isn't marginal. It's structural. We also isolated the contribution of each component. Removing the verification gate costs 2.8 points, even though every reconstruction is admitted, because unverified regenerations pollute retrieval. Replacing the water-filling schedule with size-greedy demotion costs 1.8 points. Using recency instead of advantage-weighted influence costs 1.3 points. The four-state ladder sits at the point of vanishing marginal return. 2 states forfeit 3 points, 3 forfeit 0.8, and 6 change nothing. The compute cap shows the same knee. At 0%, the deficit regresses to 6.5 points, proving that a reversible ladder without promotion compute is just a slower way to forget. At 10%, the deficit drops to 2.1. Raising it to 20 buys only 0.3 points. This isn't just a cloud simulation. We deployed the system on a physical edge cloud testbed, using Jetson AGX Thor as the hub and 2 AGX Orin agents driving robotic arms. The elastic budget cycled through the squeeze and recover protocol on device. CrystalMem restored capability to within 2 points, compared to 6.1 for Curator and 9.1 for LRU. Recrystallization latency ran at 586 milliseconds median, blocking foreground inference less than 3% of the time. Synchronization traffic dropped to 3.4 megabytes per stage, a 5-fold reduction over full fidelity shipping. Per stage energy was flat across policies. Recovering 1 point of capability via recrystallization cost 141 joules, compared to 684 joules by re-experiencing the underlying episodes. That's a 0.21 ratio. The advantage carries directly to hardware. Multi-tenant sharing also benefits. When pooling memory across tenants and fair splitting the budget, service-level violations scale poorly with density. CrystalMem's SLO-aware allocator reduces violations by an order of magnitude, with allocation decisions completing in under 25 milliseconds. The separation widens as tenant count increases, proving that sharing at density is only survivable for stores that can rebuild what the pool takes away. The broader implication is clear. Memory management for self-evolving agents can no longer treat the byte budget as a one-way constraint. Deletion and one-way compression create irreversible capability loss. Value governance optimizes survival, but doesn't close the loop. CrystalMem demonstrates that retention must be treated as reversible state assignment. Entries move across fidelity states under a crystallization energy schedule. Demotions are ordered by advantage-weighted influence with dependency coupling. Recovery is gated by invariant verification under explicit compute and byte caps. The result is a system that matches full provision capability at half the byte budget, closes the hysteresis loop, and does so with serving-compatible latency and energy overhead. As LLM agents move from research benchmarks to production workloads, elastic resource management will stop being an infrastructure concern and start being a core capability constraint. Systems that treat memory as a dynamic, reversible state machine will outperform those that treat it as a static archive. CrystalMem isn't just a memory policy. It's a blueprint for how self-evolving agents should survive, adapt, and recover when the cloud budget inevitably moves.